All right, hello everyone. My name is Michael Hall. Today I'm going to be giving hopefully a quick presentation on a brief introduction to the hyperoperation sequence. I don't know how many of you have ever heard of the hyperoperation sequence before. It's not something which we encounter even in the undergraduate content that we cover. So I'm excited to share it all with you today. So let's jump right in. Okay, so what I want to start off with is talking about counting, right? So counting is something, probably the first thing all of us have done, the first fundamental mathematical concept which we all have to learn before we can learn anything else. So counting is quite essential, right? And in mathematics, we can model counting using what we call the succession function, okay? So the successor function or operation, in this case, I'll be calling it an operation. Essentially, it's very simple. Those of you who have set theory definitely know what it is. Those of you who don't, no problem. You can probably understand what it is already. Essentially, you have a natural number, okay, as an input, and as an output, you get the next natural number, okay? So it adds 1 to the input, okay? So it's very straightforward, and you can think of it as if you're counting, right? So 1, 2, 3, you're always adding, you're always performing a successor function on that number. The reason I want to introduce the succession function is because of the next thing we're going to be talking about is, well, okay, so we're going to let a and b be natural numbers, okay? And I want to talk about the following arithmetic operations, okay? Starting off with addition, right? Probably after counting, it's the next thing we learn. What I mean by addition here isn't necessarily, adding by 1, because that's covered by the succession function. In this case, what I mean is adding by 2 natural numbers where neither of them are 1, okay? So addition is an operation which we can break down as follows, right? If we have 2 natural numbers, a and b, we can write b as a addition of a lot of 1s, essentially, right? Until we get b copies of 1. And the reason we're breaking it down in this way is because if you look at it like this, right, you'll notice that it shares quite a resemblance with the successor function, okay? So a plus 1, of course, that's just s of a. And then that output is moved to another plus 1, that's another s of a. So essentially, we can model addition, right? We can think of it as just being a repeated succession, okay, applied to a. Now, this is kind of interesting, right? We can model addition as a more elementary operator. And this doesn't end here, actually, it keeps on going. Multiplication, which is probably the next thing you learn after addition, right, is actually just repeated addition, at least when we're talking about it in terms of the natural numbers, right? A multiplied by b is just a plus with itself, right? B times in total. So there seems to be a sort of trend going on, right? We started off with succession, and then we can define addition, which is repeated succession, and then we can define multiplication, which is repeated addition. We can keep going, right? Exponentiation is the next operation which builds off of multiplication. For natural numbers, right, we can define the exponentiation of a to some power b, right, as being a multiplied by itself a total of b copied times. So again, I'm really just showing this so you can identify a pattern here. Addition is repeated succession, multiplication is repeated addition, exponentiation is repeated multiplication. So I don't think I'm too crazy here when I ask the question, what's repeated exponentiation then, right? Well, repeated exponentiation is actually defined, it's studied quite heavily, and we refer to it as tetration. So tetration, right, is the process of iterated exponentiation. So we define it in this way, right? We have, at least how I'm going to be defining it, you have a base a, and the superscript, as opposed to being on the right side, as you would for exponentiation, is on the left side of the base, right? So a tetrated to b, that's equal to a taken to an exponent of itself, b many times, right? So you have a power tower of a's, right? What's important to note here is that with power towers, right, which is what you get from tetration, they are right associative. So what we mean by that is if you're trying to expand a power tower, you have to start from the rightmost operation. So in this case, right, if we have 2 tetrated to a number of 3, that's equal to 2 to the power of 2 to the power of 2. We first work on the rightmost operation, so 2 to the power of 2, and that's equal to 2 to the power of 4, and of course that's equal to 16. So we start with the rightmost, okay? Moving on, right, we also have another interesting property, which we can pretty easily make out, right? That we can define tetration recursively. If we have the tetration of A to B, then that's equal to A to the power of A tetrated to B minus 1, okay? And the reason we can do this is because, of course, A to the tetrated to B minus 1, that's just B minus 1 copies of A in a power tower. So if we add another A to the base of that, then we get our original tetration. Here, I just wanted to show something quite interesting about tetration. I simply added one number, I added 1 to the tetration of 2 to the 3, 2 tetrated to 3, to get 2 tetrated to 4. We can write that using our previous rule as 2 to the power of 2 tetrated to 3, which we know is 16. And then we get 2 to the power of 16, which is 65,536, right? Just by adding one single digit, we get a number which is significantly larger than the previous. And this is something quite interesting about tetration and everything else we're going to see today, is that the numbers you get very quickly become ridiculously large, okay? And very quickly too. That's why we don't really see it in our day-to-day life. There's no point where we need a number so large. I mean, if you take 10 and you tetrate it to 3, the number you get is significantly larger than the number of atoms in the observable universe, right? We're talking about 10 to the power of 1 billion, when there are only 10 to the power of 80 atoms in the observable universe. So it's mind-bogglingly large. But I won't delve into how big these numbers are right now. I'll save that for the next talk. So right now, what I want to also focus on is some more properties of tetration, right? Tetration, similar to exponentiation, has 2 inverses which can be defined on it, right? With exponentiation, we have both the logarithmic function, right, which returns us the power to which our number is raised to, and we have the root, which returns to us the base, which the power is raised to. Similarly, for tetration, we can define the nth super root, right, which if x is tetrated to n is equal to y, then the super nth root of y is equal to x, and the base x super logarithm is defined as the super logarithm base x applied to y, that's just equal to n, okay? So I just wanted to highlight these. There is the reason we have 2 inverse functions as opposed to 1 for tetration, similar to exponentiation, is because like exponentiation, tetration is not commutative, right? For addition and multiplication, those are commutative operators. And as a result, if they were to have 2 inverses, those inverses can be written as one another. So let's move on, actually, because we must ask ourselves, right, if tetration, okay, is repeated exponentiation, I mean, surely we can just keep going, right? And if we do keep going, we get to what are referred to as the hyperoperation sequence. So give me 1 second. There we go. So the hyperoperation sequence is a sequence of operations which is defined over the natural numbers in the following order, right? If we start with the first hyperoperation and we allow that to be addition, okay, we can call that hyper 1 for short. Multiplication we'll call hyper 2, and exponentiation and tetration we'll call hyper 3 and hyper 4 respectively. We can then define hyper n in the following way. For any 2 natural numbers a and b, the nth hyperoperator, which we'll denote as in square brackets the letter n, then for n is greater than or equal to 2, so for the second hyperoperator or greater, we can define a hype n b as this recursive relation, where we define it in terms of the previous hyperoperation. And in fact, this is basically exactly what we did in the previous slide, where we define tetration in this way, right? Where we define tetration as being equal to a recursive relation where it's the exponent and then tetrated in that exponent, right? So we're also setting the condition here that the first hyperoperation, we don't define it using this recursion relation, but rather just as A plus B. Okay? So these are the hyperoperators, and you can imagine these will go on forever. We can have n equal to 100, n equal to 1000. In each case, we can just define them in terms of the previous hyperoperations. And in each case, the values you get by applying them get even more insane. So some rules about hyperoperations is that, as we saw for tetration, for n greater than or equal to 3, all operations in the sequence are strictly right associative. Okay? Now, this is pretty key to how we're defining the hyperoperations. In fact, the hyperoperation sequence is a lot more abstract than I'm making it seem. There are many different interpretations for what the hyperoperation sequence could look like. In our case, we're using the hyperoperation sequence that is characterized by right associativity. However, it very well could be the case that you have a sequence defined by commutativity, in which case exponentiation actually isn't part of that sequence. So there are many different hyperoperation sequences, but the main one, and the one which is most relevant to the talk today, is the hyperoperation sequence, which is defined as I denoted before. So before we move on, I'd also like to introduce a different form of notation. This is Knuth's up arrow notation. Okay, so it's quite straightforward. As it implies, there's a lot of up arrows involved. A up arrow b is just equal to a raised to the power of b, okay? Which, based on our previous box notation, is just a height 3b, right? Similarly, we can define tetration as a and then 2 arrows b, which is equal to the tetration of b, or a height 4b. If we apply this arrow n many times, okay, that's the same. We can first of all denote that as a and then up arrow raised to the power of n b, and that's just equal to a and then the n plus 2 height n plus 2 applied to b. And the reason for this is, of course, because one arrow gives you exponentiation, right? So, you know, that's why n plus 2 for n many arrows. So that's just Knuth's up arrow notation. I wanted to mention it as an aside. Another thing I'd like to mention actually is tetration as a name, right? Was Goodstein in 1947 actually came up with the name, and he extended the name even to the 5th hyperoperator and the 6th and the 7th and so on by taking the Greek prefix for a number and then applying the iteration to it. So tetra, tetration. The 5th one would be penta, pentation, and then hexation, heptation, and so on and so forth. Just a little side fact. Moving on, I wanted to go over, so this is something I wanted to cover, hyper zero, but we don't have enough time for that, so I'll just move on for now, and I'll just leave it in mystery for all of you to think about. So let's just go over some basic properties of the hyperoperations. So of course, once again, we're forcing a to be a natural number, okay? And we can derive these properties from the recursive relation we defined in the previous slide. First of all, a height n of 1 is equal to a for all n greater or equal to 2, right? The only way this isn't the case is when n is 1, in which case a plus 1 is just equal to a plus 1, right? In every other case, a height n1 is just a, right? For multiplication, exponentiation, tetration, so on and so forth. Another key property is that a height n of 0 is equal to 1 for all n greater than or equal to 3, right? I mean, think about it. Exponentiation, you take a and you raise it to the power of 0. We all know that's equal to 1. Well, this happens to be true also for tetration, pentation, so on and so forth. It's not true for multiplication and addition, of course, but this is something to keep in mind. Furthermore, okay, this is just an example to show that for n greater than or equal to 3, the height n operator is no longer commutative. So just have a simple example here where we have 2 height 3 of 3. This would be written as 2 to the power of 3, right? Because 3 is exponentiation. That's equal to 8. But if we try to do it the other way around, right? If we try to commute it, we get 3 height 3 of 2. In which case that's equal to 3 squared, which is 9. So they're not the same, right? Just one counterexample, but of course it's true for all. Maybe not all, I should correct myself. Then we have non-associativity also. As we mentioned, this specific sequence is defined just for right associativity. It's what characterizes the hyperoperation sequence, right? So we expect none of them are associative. This is once again just another example to show that that's the case. Moving on, I think it's only fair that, you know, I'm giving a maths talk, I should give at least one small proof. I just wanted to show that for all n greater than or equal to 1, okay, 2 hype n of 2 is equal to 4. Okay, the proof for this is very straightforward, and we're going to go through it by induction. Okay, so if we take the case of n is equal to 1, then 2 hype 1 of 2, that's 2 plus 2, and that's equal to 4, right? If we then assume, okay, that 2n2 is equal to 4 for some n greater than or equal to 1, of course, then we can consider 2n plus 1 of 2. And that's just equal to, using our recursion relation, 2n and then applied to 2n plus 1, which this simplifies to 2. And that's because of our previous property where 2 and then the nth hyperoperation and 1 is always equal to just the first letter number, which in this case is 2. So it remains 2. And then, of course, 2n2 is equal to 4. So since we proved it for a base case and we showed the inductive step, then we know it's true for all n, hence all hyperoperations greater than or equal to 1. So that's that, just a very small proof. And last but not least, I wanted to conclude by pointing out something very interesting. If you paid attention to my presentation at all, you might have noticed that in every definition I've given, I've only talked about natural numbers, okay? And there's good reason for that. Tetration, pentation, and all the other higher hyperoperations, things get a bit weird when we're not defining them in terms of natural numbers. Of course, we know that for the lower hyperoperations, addition, multiplication, exponentiation, we have rules which you can apply in order to determine what those values equate to, right? Some great examples, right, are hyper 3, right? We have all these very interesting, not straightforward formulae which we can obtain, none of which utilize the fact that exponentiation is repeated multiplication, right? What does it mean to raise an imaginary number to an imaginary number? You can't think of it in the same way we think of it by defining it as repeated multiplication. Same goes for e to the I pi. I mean, what does it mean to raise an irrational number to an irrational number if we're strictly using that definition? So what I'm trying to get at is, in order to obtain these more complex values, we need to create certain rules and build around these original definitions to extend our understanding of these operations. And the problem is, for tetration onwards, that becomes extremely difficult to do. It's not impossible. We have certain values, like e tetrated to 1/2, for example. That's, it's a found value. At least it's an approximated value, because the way they find it is via numerical computation. However, in general, we don't have a function which is defined over all of R for tetration. That's not to say it doesn't exist or it's not possible to define it. It's just that we're limited in our ability to figure out what that is. So it's an open problem. It's one which I highly encourage you guys to explore, right? I mean, what could e tetrated to the pi mean? We can no longer think of it as repeated exponentiation. And of course, I mean, if it's a problem for tetration, it's a problem for all the other higher order hyperoperations. So this is just a field of research which is open, active, and I highly encourage, if any of you are interested after me giving this talk, that you take a look and try to see all the different rules you can try to apply in order to figure out what these evaluate to. And I'm going to finish off here. Thank you all for listening. Hope you enjoyed. Are there any questions by any chance?
Is there any interesting geometrical or visual interpretation of this?
That's a great question. I really tried to find an answer for that myself. In general, like whenever you go searching for something like that, you're always met with the same answer, that it's like, it's too much for you to really comprehend. I mean, if we take 2 tetrated to 3, for example, that's 2 to the power of 2 to the power of 2. If we think of a cube of size 2, then its volume is 2 cubed. And then 2 tetrated to 3 would be 2 to the 4. So something to do with a hypercube maybe, but of course for larger values we tetrate to, the dimensions get larger and larger. So unfortunately I can't answer you with something satisfying. You know, it's just really large numbers which we can't really deal with very well. So that's my answer. Are there any other questions? All right, awesome. Thank you very much.